Hi all, this is lecture 23. We are in section 4.7, I believe, on optimization. We did the first three in class, so I'm jumping in here at number 4. I'll post these solutions, so if you missed 1 through 3, you can take a peek at them there. But we have an aluminum soda can, which is shaped like a right cylinder and holds 12 ounces of liquid. The production of aluminum requires a lot of energy, so it's desirable to design soda cans that use the least amount of material. What dimensions would such an optimal soda can have? So if we've got a soda can, okay, and our soda can is going to have dimensions involving its radius and its height, okay, and I have the value 12 ounces. It can hold 12 ounces of liquid. That represents its volume. So my constraint is going to be the volume. And the volume of a right cylinder is the area of the base, which is pi r squared, times the height. So pi r squared h. And feel free to look that up anytime you like. Okay, and I know that's going to be 12. So I have 12 equals pi r squared h. Now, I don't really want to solve for r here because I've got that square. So I think I'm going to solve for h. So I'm going to divide both sides by the pi r squared. And we'll deal with the fallout of that later. So we have h equals 12 over pi r squared. And then we want to write our optimizer. So our optimizer is what we're trying to find the optimization of. So we're looking for a can that uses the least amount of material. And the material to build the can is on the outside. So that is its surface area. So the surface area here, if you think about your can, you've got a circle on the top and a circle on the bottom. So each of those circles has area pi r squared, and you have 2 of them. So you have 2 pi r squared. And then you have the area that is that kind of middle that's wrapped around. And if we unwrap it, it looks like this, where this is the height. And this was wrapped around the circle. So this is the circumference of the circle, which is 2 pi r. So that means I'm going to have 2 pi r h. And now you can see I did a good thing here by solving for h because I only have one h to sub for. So I can sub that back in. So if we do that, if we take this and bring it over, then we have the surface area is equal to 2 pi r squared plus 2 pi r times 12 over pi r squared. And if we simplify this, the pi's cancel and one of the r's cancels. So what we end up with is the surface area equals 2 pi r squared plus 2 times 12 is 24 over r. And now we're going to go ahead and take the derivative because we're looking for the least amount. So I want to minimize the surface area. So the derivative here would be 4 pi r minus 24 over r squared, right? Because you have r to the negative 1, multiply by the negative 1, subtract by 1. And we're setting this equal to 0. Okay. We can make this 4 pi r is equal to 24 over r squared. And then let's multiply both sides by r squared. By having my r on the bottom, it does mean that r can't be 0, but if r was 0, then we wouldn't have a radius and we wouldn't have a can, so it's okay. So this is 4 pi r cubed equals 24, and then let's go ahead and divide by the 4 pi. And this is going to give us r cubed is equal to 6 over pi. And we'll just take the cube root. Now, we don't have to do plus or minus here because we don't get 2 answers, right? When you take the cube root of a negative, it's negative, and we don't want that anyway. So this is going to give us r equals the cube root of 6 over pi. Okay. Now, if we put that into the calculator, 6 over pi is 1.9, and if you take the cube root, you end up with 1.24. So just in terms of reference. Now, I don't really want, I guess we could go second derivative test here, but I kind of don't want to. We could. Let's go for it, I guess. All right, so from here, your second derivative, and actually I'm going to put it down here to be consistent with what I was doing in class. Your second derivative is going to be 4 pi from the first part. Now you have 24 This is the same as 24 r to the negative 2. So that's going to be, and that's a minus, so that's going to be plus 48 r to the negative 3. So you're taking 4 pi plus 48 over r cubed. Now, 4 and pi are positive. When you take 1.24 and take 48 divided by that, that's all going to be positive. So this is going to be positive concave up, which means you get a local min right there at the bottom. So we did find the local min. So my radius is 1.24. All right, now we're going to take that over here, bring that back and plug it back in. So that means that h is equal to 12 over pi times the cube root of 6 over pi squared. And let's see. If we plug that into a calculator, your height turns out to be 2.48. Okay, now they're asking what dimensions would that optimal can have? And so the dimensions, so the can would have height 2.48 and radius 1.24. Now, I'm not really worrying about units right now just because they give it to us in ounces, and ounces you have to do some conversions to figure out what the distance measurements for that would be. We'd have to kind of convert that to probably maybe cubic centimeters or something like that, and then we could figure out how many centimeters or inches or something like that the height and the radius would be. So we're going to leave the units off for now. But note that the height is double the radius. So essentially the most optimal can, the radius across, the diameter across the top is the same as the height. So it almost is like a perfect square, a perfect cube, as cuboid as you can make it. It's just not very useful in terms of drinking it. So they do have to alter it. So that's not what our typical cans are. So our cans that we use for soda is not going to be the minimum amount of resources used. All right, and then lastly, number 5, a stone is thrown straight up from the roof of an 80-foot building. The height and feet of the stone at any given time t is given by this equation. What is the maximum height the stone reaches? So we are going to take this equation for height, and we're going to go ahead and find the max. So we can go ahead and jump in and take the derivative here. So h prime of t is negative 32t plus 64. Let's set that equal to 0. And we're going to get that t equals 2. Now let's go ahead and take our second derivative to do our second derivative test. And that's negative 32, concave down, local max. So we do have the max. Now, here's the problem. This is my t value. And this is likely in feet per second would be my guess. So this is going to be in seconds. But it says, what is the maximum height? I didn't find the maximum height. I found a time when the maximum height happens. So in order to find the height, I've got to take my t and I got to take it back here and plug it back into the original. So I would find the height at 2 to be negative 16 times 2 squared plus 64 times 2 plus 80. And that's going to give you, let's see, 4 negative 64 plus 128 plus 80, and that's going to give you 144 feet. So it's going to go up to a max of 144 feet and then come back down. And so our final answer here is that the maximum height is 144 feet. Okay, and then we'll work on the rest of the problems in class.